Welcome to Unfair Fights. Tonight we're going to be talking about, is Redshift good evidence for an old universe? Does it cause me a problem for young Earth creation? And my brother Nathan is here, and he's going to be hitting me with as hard as he can on that topic. So, how you doing, Nathan?
Doing great. Glad to be here. Can't wait to smash the young Earth creationist view. So we'll see how it goes.
All right. Well, let's see if you can do it. Well, it's funny because last week you were saying when we were young, I would ask Dad questions and he would always give me scientific answers. And when you said that, what you meant was old Earth evolution answers. But I talked to Dad this week. He doesn't believe in evolution.
Well, I guess I guess you can believe in the old universe and and believe in evolution and believe in I don't know. I don't know. I guess, can you really believe in old universe and not believe in evolution? Yes, I guess you can. But I guess what I was saying is that when I would ask Dad questions about the age of the Earth, he would give me ages that were in the scientific consensus. Like for instance, the top of a mountain that had some shells and fossils and stuff mixed into the limestone cap of the mountain. He wouldn't say, "Oh, that's 6,000 years ago." He would say that that's from an ancient sea millions of years ago. So I'm not sure. That's what I meant.
Yeah, it is kind of, it can be inconsistent. It does kind of come together in a package deal, in my view. But there are some people who, have sort of a mixed view there.
Well, that's
So,
one of the interesting questions for today, because I'm interested to probe and see exactly where your creation comes into play. So this episode, or the stream, we're doing the cosmic distance ladder, and we're going to get to the redshift. That's going to be the bulk of the information. But I was wondering if somewhere along the lines there you're going to have a problem before then. So it'll be interesting to see.
okay, so do you want to just go ahead and introduce our topic?
Sure. So in the old universe view, the universe is 13.8 billion years, and that number has changed a little bit over time as new data has come in, and our ability to sense and with precision the universe has improved. That number has changed a little bit. But essentially, scientists now believe that 13.8, or scientists, sorry, I keep using these pejorative words, the old universe group believes that this is, 13.8 billion years. It came from, the Big Bang model, where, today the guy I'm going to talk about, the original guy called it l'atom primitive, like a primordial atom, some sort of small singularity or compact object that then expanded rapidly through inflation to the present day. And so that's kind of what we're challenging here, is the idea that the universe was created 6,000 years ago, or on some sort of biblical Genesis timescale. And
Okay.
shall I just get into it? Shall I just
Yeah.
go? I mean, okay, if you could share my presentation there. All right. So in 1909, Henrietta Leavitt was employed as a human computer at the Harvard Harvard College Observatory. And this is Women's History Month. I think it's still Women's History Month. Is that correct, Becca? Is it still Women's History Month? Um, But you might be surprised to see all of these women corralled into a small room performing math. Yes, women can do math. And one of them was Henrietta Leavitt, and she was looking at information, photographic plates taken from a telescope for the Large Magellanic Cloud. And at that time, one of the debates in science was whether these spiral nebulae that were seen were inside the galaxy or whether it was something far away. And as she was observing this data, she realized there was, and here's a, and there's a picture of her.
Oh,
This
did
is
you
her.
move that or did I? I'm sorry
You
about
moved
that.
it.
I
You
was
moved it.
trying
It's
to
all right.
move it off of your face, but anyway, go ahead.
So she's third to the left there. Interestingly enough, she was also deaf. She had an illness and got deaf. So yes, deaf people can also do math and make extraordinary scientific contributions. And she was also a Christian. So it's late in her life, she still went to church, was very active in her church, and so yes, she was also a strong believer in Christianity. So here's another picture of her. And what she found when she was going through this data was that the maxima and minima of these stars, so there were certain stars that would kind of get bright over time and then fade. These are the Cepheid variables, and there are multiple types of them. But anyway, so she's found a correlation or basically from the magnitude of the brightness. So that's the one on the left side there, and the period. So the time from when it goes from a maxima to a minima was related. And she made a simplification saying, okay, if all of these stars are roughly the same distance in the Large Magellanic Cloud, then we should be able to measure a Cepheid variable that's closer to Earth using parallax, and then use this other one as a standard. This local one is a standard candle and determine the distance. And so these are the kind of the first two rungs of the cosmic distance ladder. The first one is parallax, and the second one is the standard candles. Now, interestingly enough, when this paper was published, the person who employed her, the astronomer who employed her, had to put his name on it and sign it in order to get it published, or they thought that was the only way they were going to get it published because of prejudice against women. But it was clear from the first line where he said, this was prepared by yada yada, and then she writes the rest, that she was actually the person who found this information. Later on in life, someone in the Nobel Prize committee thought, hey, we should give her a Nobel Prize, but she had already been dead for 3 years of stomach cancer, so she never got her Nobel Prize. But this revolutionized astronomy and our view of the universe at the time, because before that, a lot of people believed in steady state theory, or they believed that only the galaxy was that's it. It's just the galaxy that we're in, and this kind of took us out of that. All right, so here's here's an image by, I wanted to go ahead and give this guy credit, whoever he is, Thomas Vibe from Wikipedia. Thank you, Thomas Vibe. But here's an image of a commonly used Cepheid variable, and that's delta Cephas. Okay, and what you see is over the period of 5 days, it goes from a maxima to a minima, and then back to a maxima. And this is one that they can use for a standard candle. So just very briefly, I'm going to go through this real quick because I want to get to today's topic. Parallax basically it uses the distance from when the Earth is on one side of the sun to the other side of the sun to take two images, or more than that, I guess, over time, and to determine how things shift in the sky. So if something is closer, it would shift more, and if something is farther away, it would shift left. So that's parallax. That's the first rung. And this is a image from the Gaia probe, which is revolutionizing our view of the way that galaxies form and all of that. And it has now extended parallax to 31,000 light years. And this image here is from New American, and it was basically an image of, what scientists or what old universe people think the Milky Way may look like. And overlaid in it is the whether objects are moving toward the center of the galaxy or further away. That's another piece of information that Gaia has provided. So I'm just going to briefly go through two more things, and then we'll get to our topic for today. So no problems so far, Rebekah, right? No problems with 31,000 light years. Is that problem? No. Okay. Oh well, this should be interesting. Maybe at the end of this, we'll just be in total agreement, and we won't have had to have this discussion at all. Okay. So next one. So this is Erwin Hubble, and we have. A modern picture kind of on the left. We have a Hubble picture, which is kind of a zoom in, I guess you could say, of the Cepheid variable he found. And then on the bottom right, we have his original picture where he was looking at some things. He saw some bright things, and he'd marked them nebula, or not nebula, nova, right? Because he thought that they were novas. And then he scratches out the one in the upper right, and he says VAR, variable, because he had realized that it was actually a variable star. And that allowed him to use the information that Henrietta Leavitt had provided to determine that no, Andromeda is not a spiral nebulae inside of our galaxy, but it is another galaxy far away. And he overestimated I think how distant it was, but basically it's on the order of millions of light years. Okay, any problems so far, Rebekah, with any of that? So
Nope.
now we're at millions of light years, unfathomable distance. Okay, so now we come to today's topic, which is redshift. So beyond the standard candles and that kind of thing, we have another phenomena that Lemaire and which one I'm going to go in, or Lemaitre, whatever, and Hubble. This when they noticed, and other people also noticed this as well, that some of these spiral nebulae that we now know are galaxies outside of our galaxy are traveling away, or I won't say that. I'll say they are red shifted. I've tried to remove all of the details of this graph so that Becca can experience it without these predetermined scientific consensus ideas. Okay, so we have a redshift on the left, and on the bottom I had to substitute distance for something else, and so I said magnification needed to see an object clearly. But maybe that's also loaded. I don't know. And what we see here on this page are some points that are spiral nebulae or galaxies. And then we have some that are above and below the redshift line, which I thought she might find interesting, or maybe you do too. And that is the Virgo cluster. Okay, and then we have some more after that. Now, what is a redshift? I'm just going to go this real quick for our viewers. They probably already know, but anyway, when light when atoms get excited or molecules get excited, they jump from one orbital to a lower orbital after they emit light, and there's a pattern to that. And these little bars here show a certain type of light, or a spectrum of a star or whatever, or galaxy or whatever. And as you go towards these more blurry reddish ones, you can see that that certain lines of elements, primarily hydrogen and helium, get shifted to the right, or to the red end of the spectrum, or to the lower energy part of the spectrum. Okay, and just to give an example, so this is two pretty extreme examples of this redshift. So the one on the left is a galaxy in optical light that's very close, quote unquote. So far we could never get there. Even Star Trek people don't get there. Traveling at warp 9. And then on the right, there is one that is very, very faint, very, very small, and is shifted way to the red, so that you have to have a different type of telescope, this type, the James Webb telescope, to look at this infrared light. And maybe you can't see it because the picture's small, but there's other bigger ones closer in the image, and then far, far, far away you have this little tiny pinprick of light, and expanding that, you see it's also a spiral galaxy. And here, finally, last image for a while, I swear we'll actually start talking now. I'll give Becca a chance to explain how all of this goes into her theory or her hypothesis or whatever. And here's the Virgo cluster. So that was on that graph. You saw some of them are more red shifted than others, and some are blue shifted. Science. Here comes some blue shift galaxies. And so I wanted to show a picture of that as well. And so that's just thousands, many, many, many galaxies, all kind of together, orbiting each other, and lots of galaxies all in one place. Take it away, Rebekah. What do you do with this? Which slide do you want? You want this one here? Do you want any of them? Should we just take it off? I can't hear you again.
Oh, sorry. I don't need the slides. We'll put them back up there if you have a point to make. So first, what should be understood, and we're talking about the redshift tonight, so I will start with that. Okay. So there is definitely a correlation between the redshift and distance. So objects that we observe that are farther away are seeming to be more shifted to the red, and so that is absolutely true, and that I'm not questioning that. What I am questioning is our interpretation of the redshift, which currently in the standard model, the interpretation of the redshift is that it's caused by these galaxies all expanding, space is expanding, and so they are moving away from us. So is that your understanding, Nathan?
Yes, I do believe that the universe is expanding.
Okay. And so that's the current explanation of the redshift in the standard model. But what should be understood is that is simply an interpretation of data, and there are other interpretations of the redshift, and I think that there are some that make better sense with our other observations. For example, there are the idea that redshift is actually just a product of something happening to the light as it is getting to us. So there's, some different ideas. And remember, Nathan is ambushing me tonight, so he gets to do all the research. I don't get to look up anything. So all of this is just stuff that I remember from looking at this before. So I'm maybe totally butchering these different ideas, but there's one about Wigner crystals, and somehow there's some interaction with light, and that's causing the redshift. There's, the idea of, light as it's going through plasma it's appearing to us as red. Do you want to interrupt?
No, I don't want to interrupt. I want to give you your chance. At Wigner crystals, I'm very interested in Wigner.
Well, I can't go farther on that, okay? But
okay.
So.
Oh, what? I don't get more? I don't get more about Wigner crystals?
I don't,
You're just going to invoke Wigner crystals?
I'm just telling you these are different possibilities for the redshift. Now, right now, we don't know for sure what causes the redshift, but I do think we can safely rule out the expansion of the universe. First of all, I don't even know that we have any observational evidence that the universe could even expand, right? So that is something the idea is come up with to avoid another idea, because like one of the ideas that if we see the redshift, it would kind of give us maybe the idea that things are all moving away from us. But if they're moving away from us, then and that really puts Earth in the center of the universe, and that's problematic for, people who don't believe that Earth could be that special. So, and I don't believe that things are all moving away from us and that Earth is in the center of the universe. But I also think that our observations do not show that space is expanding. And so I'll talk about a few of those. Well, I'll talk about the main observation that we have about that. And that is that the Tolman surface brightness test. Okay. And I've tried to think hard this week on a good way to explain this in a short amount of time, where people who are watching who have not looked into this can figure out what's going on. Think of it like this: when we look out into space, right? Just like when we look out into the distance, we have perspective where things that are farther out are smaller and generally not as vivid, right? So there's a definite progression of how that happens, and we try to capture that in paintings. We try to capture proper perspective. Well, when we look out into the universe, okay, it looks that way. And so and that as we look out into the universe, the farther that we've looked out, we see some things that we shouldn't expect, because as far as we look out, and the first time when we really noticed this, to the degree that it caused a problem for the expansion of the universe, was with the Hubble telescope, because we did not expect to see galaxies preserving that distance perspective, but they do. Okay, so and I'll explain why they shouldn't if the universe is expanding. But as far as we look out with the Hubble telescope, we see at the farther away it is, the smaller it is, the dimmer it is. And then with the James Webb telescope, same thing. The smaller it is, the dimmer it is. Now, this has been observed using the Tolman surface brightness test. Okay, and those should not be our observations if the universe is expanding. Why? Because if the universe is expanding and that light has really taken the time that Nathan thinks it has taken to get to us, then when the light left, it's the galaxy was actually closer to us. Okay, so at some point, and I couldn't look up what the actual distance turnaround point is since I wasn't researching it, but people can look it up. There's a certain point at which there's a turnaround if we consider the expansion of space, because now these objects are farther out and they would have been larger when the light left. So we have to factor in for that. Now, when we do those calculations, something very weird, we have to do something very weird to our observations, right? When we try to factor in the expansion calculations to our observations with the Hubble telescope, with the ALMA array, and with the James Webb telescope, we end up with those factors, we end up getting galaxies that are not like any galaxies observed in our local universe. They are much smaller and much brighter, much denser. Okay, and if you look up Eric Lerner, you'll see he has calculated what can be the minimum, like the smallest that a galaxy can possibly be before it will have a gravity problem, right? And these galaxies that we're seeing out there are way too bright. Like there's one GHZ2. I'm not actually sure about that. I think it's GHZ2. You can look it up. But if when we put in the expansion calculations, that makes that galaxy be 14,000 times brighter than any local galaxy. Okay, it doesn't make any sense to, when we look out at those galaxies, we're seeing spiral galaxies and types of galaxies that we see in, our local area, local, being still very far away. But, it doesn't make sense when we put in the expansion calculation. So I think we have good reason to think the universe is not expanding, based on that. And then I think one of the problems.
Hold on. Okay. Maybe we can address a few of these problems
first. Okay.
in turn. So one of them you mentioned was plasma. So
Okay.
can you hear me okay?
Yes.
Yeah. So one of them that you mentioned was plasma. And, the intergalactic medium, what is there? Scientists are aware that this changes the observation. So first of all, in the Hubble equation, there are two things. There's one of them is called the sorry, I should have. Well, also first thing, real quick, if there are any unfair friends for Rebekah, please help her out, because again, she was not able to research, and I know that she's read a lot about this, she's thought a lot about this, but in terms of the specifics of, she said something about Lerner and some sort of crystals. So if you guys have some information on that, you can post that, and then we can find out what these crystals actually are, because I'm just thinking like crystals out there, ooh, crystals out in space, but
okay, look, Nathan, just look that up later. We're not going to talk anymore about that, but
okay.
But you can look up what I'm saying about the Tolman surface brightness test and our observations that are against expansion. And I do remember there's a paper by Ricardo Scarpa and Eric Lerner on that. So look that up.
Okay. Well, so two things real quick. So in the Hubble equation, we have recessional velocity, which is the redshift that scientists are attributing to the universe expanding. And it's, you mentioned that the Earth is in the center, but actually
no, I didn't say that. No, I did not say the Earth is in the center. No, I said I'm trying to explain, why did we come up with this whole idea about the expansion of the universe? And it's because we were trying to figure out a way that we could get everything to be accelerating away from us without putting us at the center of the universe. So we came up with this idea that, possibly it's expanding in all directions. Okay.
Okay. Oh, yeah. Okay. Gotcha. So just to make that clear, yeah. So you don't believe the Earth is in the center, but scientists, or not scientists. I'm sorry, I'm using this picture. Old universe people are saying that the universe is expanding, but it's kind of like bread rising. So two raisins on a piece of bread, as the bread expands, would get further and further away from each other. Okay. So in the Hubble equation, we have recessional velocity, which is that velocity which is attributed to the expansion of the universe, and that's what scientists are kind of fighting over in terms of what is this Hubble constant, because they have two different values that they're trying to merge together. That's called the Hubble problem. And then we have peculiar velocity, and so scientists do account for certain particular things. So I had the Virgo cluster on there. There are a couple different types of things that can impact it. One is called the finger of God, interestingly, and that's related to distortions that can occur, I think, from things rotating. So we have things rotating around each other, and so
what does this have to do with anything, Nathan? Get to the point.
Okay, all right. Well, anyway, all that all that to say that scientists are paying attention to plasma, intergalactic medium, and things rotating away from us or toward us, and trying to factor that into their calculations. Now, the thing I really wanted to say, and I think is the elephant in the room, okay, we can talk about problems in current cosmology or questions, like, for instance, that spiral galaxies look more mature than they thought, or are brighter, or and that is open questions in cosmology. But to me, the big elephant in the room is you're kind of trying to paint in all these, there be dragons here, I'm going to fill that in, but you still haven't explained how the universe is so big and how the light is reaching us how old do you think the universe is? Is it only 6,000 years old? And if so, how does the light get to us? How do we even get to Andromeda? How do we even get outside of our galaxy? Because as soon as you say, um, you know, that Andromeda galaxy is 2.5 million years away, to me, you're an old universe person. You may
Yeah.
not believe in the current standard model, which I think you should, but you're an older universe person. You're not a young universe person at that point, to me, unless you have some explanation.
No, yeah, I'm about to get to that, and I was getting ready to get to that, but you actually stopped me to question me about the
Well,
redshift.
you were rambling
Oh,
on for a long time about crystals
okay.
and
All right. Okay.
naming
Now,
galaxies and Hubble bright or
okay,
some
let's
sort of
get to
surface
it then.
brightness of something.
Let me ask you, Nathan. So, in I'm not disagreeing with the distances. Okay.
You're not.
But
Okay,
no, I'm not.
interesting.
But do I think the universe is billions of years old? No, I don't. Okay,
What's the
but
difference between
what
millions and billions?
what?
What's the
Did I
difference
say
between
millions
million?
or billions?
No, you said billions, and I said
Yeah.
Andromeda is 2.5 million light years away,
Yeah.
and you had no problem with that.
Right. Okay, so how are you measuring the light? How long now my understanding is that light travels at 186,000 miles per second. Is that right?
I
It's
think
been a
so,
while
around there.
since I looked it up. Okay,
Yes,
but
yeah, yeah.
I want to know how you're measuring how long how are you measuring the speed of light? How are you measuring how long it takes the speed of light to get to Andromeda to us?
So in my example earlier, it was using a Cepheid variable star, and so
Now that's
they.
telling us where the distance is. That's not telling us how long it takes light to
Okay,
arrive to
okay.
us.
So that's good. Okay, so why is the speed of light what it is? And if you could share my presentation again, real quick. I'm just going to flip forward to this. Okay, so these are some equations that engineers use all the time, and I have to say, I want to just give some credit where credit's due. This guy Alvin Ash did a video on James Maxwell that I watched that was just fantastic. So if you get a chance, check out Alvin Ash science video. But basically, Maxwell was looking at these equations regarding light, the way not light, but electricity and magnetism. And people had already determined that that magnetism is affected by electricity, and vice versa, but nobody had put them together. And you'll notice that in one of these equations, there's E naught, and in another one, there's this U naught, or it's a Greek letters naught. And these are standard constants that people measured, and one of them is related to the permissibility of space to magnetism, or kind of like, let's say if you were taking a stick and you were pushing it through water, permissibility could be thought of as how hard it is to push through the water, right, with a stick. That would be the permissibility of water. So we have these two constants, and Maxwell sat down and thought about it, and he thought, okay, one is I know I'm boring you with all this
Yes, you are.
math
Nathan,
talk,
this is like
math,
way
math.
off topic. Just get to the topic.
No, okay, all right, fine. All right. So basically, what he determined was that they are related, and that the carrier particle for these two things is light. So electromagnetic radiation. It's given by an equation of those two things that people had already found, which is U naught and E naught, and it's divided by one. So if you change the velocity of light, not only do you affect light, oh yes, light, no big deal, just going to change the speed of light or whatever. But you actually impact all of these physical constants for electromagnetism. And frankly, I think that you also impact the weak force, because that is related to magnetism through symmetry breaking, and also the strong force, because it's related to the mass of a particle that's emitted in the strong interaction, and uncertainty. So you would change all of the physical parameters of the universe. When you mess with light, you mess with everything. And so good luck messing with light here. You're just
No,
like, oh
I'm
yeah,
not messing.
it's far away. It's far away. But how do you know that it's old if it's far away? Well, light has to travel at a certain speed in order for the universe to work.
And
But
I'm asking you, how are you measuring that?
well, I think the speed of light was first measured in the 1700s. I don't have that information on me, but Maxwell, when he was doing this calculation, he realized what could be this value, and he came up with this value, and he realized this was the speed somebody had already measured for light, and then the light bulb went on, bing, light, and he realized that the wave that he was talking about for electricity and magnetism was actually light, which is pretty phenomenal, for somebody to think about that. And it was only proved about 40 years after, 50 years after he came up with that. So it was really a thought experiment. So
Okay,
anyway, I think
so
the speed of light is a constant. I think
yeah,
to mess with
and
it, you're
I'm
going to
not
mess with a
arguing
lot.
with that. I'm not arguing with that. But this is really interesting that Stephanie put, I have a friend. So she says, ugh, light is instant. The theory of light speed is actually theory. Now, what's interesting is that this is one of the proposals, and there are a few proposals for how light reaches us with, from such a far distance. But one of them is the understanding that every time we measure the speed of light, we are always measuring the two-way speed of light. You have no way to measure the light in one direction from here to Andromeda. You have no way to see how long it takes light to go in one direction from here to Andromeda. You only know how long it takes light to make a round trip. Okay, every measurement of the speed of light is two-way. And so
What do you mean by that two-way? Explain that a little bit.
well, what I mean is we don't have we would have to have synchronized clocks, right? And one clock would have to travel a distance, and then we'd send light, right? And then we'd have to know that they stay synchronized. Okay, to be able to measure the one-way speed of light, we'd have to make sure those clocks stayed synchronized, and then we could, basically measure that. But we have not been able to do that. We have only measured the one-way speed of light.
But
So
every time you use your phone, people are having to make modifications based on the theory of relativity to make sure everything works right, because the satellite in orbit around our planet is impacted by its velocity, and so we're using light all the time, and the speed of light is being used all the time, and it's used. The speed of light, and like I said, impacts everything. The way that an atom emits light is dependent on the speed of light. Everything, every scientific thing, and I think it's interesting that the Bible also puts that on day one, let there be light, and that for some reason the speed of light is so fundamental to all of these old universe scientific consensus ideas that we use every day. It's the when you turn on your TV, when you use your cell phone, the speed of light is involved in all of that. And so to say we don't really know the speed of light, or I think it's
no,
I think it's weak sauce.
I didn't say that we don't know the two-way speed of light.
Okay, so
Okay.
we do, or we
I'm
don't know the
saying that
two-way speed of light.
we do.
We do. We know. I don't
Yes.
even know what two-way speed of light means, but okay.
The way that light travels in, like, it goes out and it comes back. Okay.
Okay, like bouncing it
So
off a mirror.
yes. Okay. So
Okay.
and I believe it was Einstein who came up with the convention of making the light go the same. I mean, he decided to use the convention that light would travel the same speed in all directions. And so that's the convention we've been assuming. But it is just a convention, and Einstein admitted that. And Einstein actually said we were free to use other conventions. So the convention I'm proposing is that light travels instantly as it's arriving to us. It doesn't, it comes to us immediately. So I'm seeing the universe as it is at this moment. And so it doesn't take the round trip still will be, you know, the C will be the same, but it will not.
But
But
but what's the
this
difference
does,
between me sending light to a satellite and it traveling at the speed of light and then coming back at the speed of light, so that your phone works? Why is that any
because
different
you
than a
only
galaxy?
know, yeah, because you only know how fast it made the round trip. You don't know
Oh,
how fast it went out and came back.
this
Okay,
this call that we're on right now, this call that we are on requires the speed of light to travel the same way, one way across the Atlantic, or one way across the world, or one way up to a satellite, and one way back down, at the same speed.
but
If
how do you know? What are the
How does fiber
scientific
optics work?
observations that let you know what the one-way speed of light is? You know the two-way.
No, no. I mean, we're two people. We're two conscious beings on the opposite ends of a conference call or whatever this program is, right? So how is it that it would travel one way to me and then go back one way to you and be instantaneous for you, but for me it's not instantaneous? Light actually, from the perspective of light, it's always instantaneous, which now that's a mind-boggling idea. I don't know how that works because I'm not traveling at the speed of light. But the light is always the same, and the time that elapses for light is actually zero.
Okay, so if you're saying the time that elapses for light is zero, why do
yes.
you have a problem with the convention that I'm proposing?
Well, because matter that's emitting the light and the distance that it's traveling is not at zero. It's Time is happening. For all of us massive particles, time actually happens. So, you know, I think that light being instantaneous from the perspective of light is a mystery to me. It's a mystery, and I admit that. The fact that light does not is not affected by time, it doesn't decay because it's not affected by time, is a mystery to me. And I think it's an open mystery. But the way that light travels through space time is not a mystery. I think that it's very and that speed of light is a mystery. Why it's that speed is a mystery. And people say, oh well, there might be other universes where it's not that speed. It's something else. But it would be very hard to understand how we could exist in this universe if the speed of light was not what it is, because it is underlying every equation that scientists use and engineers use every day.
But do you see what you keep doing? You keep saying, if the speed of light is not what it is. I am not arguing with the C, okay? I'm not arguing with the value of C. I'm arguing with the convention of assuming that there's a two-way split, like that it's split equally on a round trip, that it's split equally, that light will travel in the same way in all directions.
But scientists don't think that. Actually, they think that if I bounce light off in the Andromeda galaxy, the because it's coming toward us, it would take less time for that light to bounce back. So that's a blue shift, right? So scientists, I mean, I keep
Nathan,
saying
you
scientists,
can't
but
look, you put,
old universe.
let me just say right here, because you keep saying scientists, and I know you're trying not to do that, but I just want to let you know that there are scientists who tell me, now I have to take their word for it because I haven't studied this in depth, but there are physicists who tell me that this thing that they have proposed, that this convention that I'm telling you right now, is totally in line with physics. And if you go on and try to look up, a problem with this, you won't find a problem in physics with what I'm describing. It is perfectly in line with physics.
Yeah, I think you cut out there for a second, but yeah, you're saying it's perfectly in line. And to be honest, I don't know if you have described what you think about it clearly enough that I could address it. Like by saying two-way or going this way and that way. I actually don't know. I don't know. I understand what you're saying, right? Um, Enough to address it. But I can say that I think that changing the speed of light is not a good solution for a young
I
Earth.
didn't change the speed of light.
Well, if you're saying that it
I
goes,
didn't change the value of C. I
okay,
changed the convention that we're using, which is the distance that we're saying right now that the round trip's speed of light should be divided equally so that light travels the same speed in all directions, which is a convention.
well,
It is not, we
I,
don't have observations
I,
to show that that's true.
no, what science? I mean, what if you believe the theory of relativity, which we use, like I said, for satellites and stuff now, then the speed of light is always constant at that speed, regardless of how fast you are traveling. And that's why, because of that, because Einstein knew that it was a constant, he had to come to the conclusion, and this is where his genius came in, that something else had to change, and that was time would have to change. In order for the speed of light to remain constant from every reference frame, whether you're traveling from, 100 miles an hour or a million miles an hour or 10 million miles an hour, the only way that the speed of light could remain constant was if the time of the observer changed. And so that was the genius of the theory of relativity. And it's a very bizarre finding, but we do find that it is true. And so,
Well, if that is true, Nathan, then there may also be a solution with the distant starlight in relation to that, right? Because then time is affected by gravity. So if there's, if Earth is in a gravity well, then we could be experiencing the light arriving to us, in a different way than, right? Like since time, if you're okay with this idea of time, being uh, so strangely, like,
malleable.
yeah, that good word, malleable, then why are you giving me such a hard time about how long it takes light to arrive to us? The time is malleable, right? So
Well,
why pick on this? You don't even know,
what
we don't even know what light is actually. Light in its nature is contradictory, right? So why give a hard time? Why try to say it's impossible when, like, it's
well
impossible that we have a young universe.
Well, I mean, one way to look at it, all right, one way to look at it is that by saying the world was created in 7 days, you're just asking how fast God was traveling when He created it, because there is a reference frame where the universe only took 7 days. But the reason why I'm doing it is because obviously, um, there are certain people who see it as a threat. Oh, the universe being old at our reference frame of movement must mean that the Bible is not true. And so I cannot believe that the universe is billions of years old. And to me, that's what's underlying the whole proposition. And so people are coming up with ideas. And let me just say, let me take a step back. I actually appreciate the out of the box thinking, even the crystals and stuff, because I think that out of the box thinking is needed. One of the things that's going on right now is this idea that we're all a hologram, that we're all somehow, a two-dimensional surface that's being created three-dimensional, you know, by geodesics or whatever. And so there is this idea that we don't understand what dark energy is. We don't understand what dark matter is. There are, like you said, you pointed out that there are problems with, before the Webb telescope, people thought, okay, we're going to look out there and we're going to see one thing, And then they look out and they find spiral galaxies 1 billion years after the beginning, and they go, well, this is not fitting our models. And so now they're having to go back and look at it and think about it. They see supermassive black holes that are bigger than they expect, and that's making the universe, the galaxies brighter, like you said. And so people have to go back and rethink about what they think about the beginning. But I think that most of the people in the scientific community would think that whether it's 13.8 or whatever, they're not saying that 6,000 years ago in our reference frame, the Earth was created, and so I guess the proposition that it's a danger to people, danger to their belief system. Um, you know, I don't know if we want to show a slide this
No,
late.
we're not. What? Sorry,
I don't
go
know if
ahead.
we want to show a slide this late, but the guy who came up with the first Big Bang theory, he called it, like I said, he called it l'atomic primitive. Uh, let me just, I'll just scroll forward here. But it just disappeared. Anyway.
Oh, sorry. Here you go. Okay. I didn't see it.
Okay, so here's the
Okay.
guy in the middle, and his name is Lemont
Whoops.
or something like that. Anyway, he was a Belgian priest. He's shown here with Einstein and some other guy, possibly from Caltech or whatever. But anyway, he actually came up with this idea that things are receding 3 years before Hubble, and there's been a movement to try and get him added to that name, the Hubble constant or whatever, or Hubble law. And he published it in French, and then it got translated in English. And he used Hubble stuff when it got translated because he thought, well, his data is better, which it was because Hubble had a bigger telescope. But anyway, he was a priest, and he's the first one who came up with the Big Bang theory. And the Pope at that time praised him for showing that that everything came into being in a moment, because among the scientific community at that time, at least in the 19th century, steady state was all the rage, where or that the universe was forever, that it was a forever thing, and the idea that it was created was, or that it came from a single point in time, was anathema to scientists. And so I think the idea that the Big Bang is somehow scary to Christians or believers of any faith, I think it actually shows that it's true, that the Bible's true.
Well, I appreciate that perspective, and nobody ever said anything about being scared about it. Okay. I'm not scared about it. I just don't think it's correct. And I mean, we can go another time, we can go into talking about all the problems with the Big Bang, because I don't think the Big Bang can hang on much longer. But that's not the topic for tonight. I think we're at a good stopping point with this, where you can but anyway, but I want to introduce the topic unless you have a final thought.
My final thought is, please help me next week, my unfair friends, because I think we're about to go into evolution, and I feel pretty solid with cosmology, but with evolution, not so much. So, from this point, from the announcement, I can do no research. So hear me, unfair friends, hear me, please. Do a little research on your own.
Yes,
Help me
I
out with
would
this.
love for anyone to do research on this and show up with something for us in the chat. But I'll tell you, the thing I picked, I don't think there's any evolutionary explanation for it. I can't find one. So good luck. Okay. The topic I picked for next week is butterfly evolution. Okay. And I want to set this up a little bit for you guys. And I need to make this smaller because this is just too annoying. But I want to give you an idea about the problem so that you can start thinking about it, because even if you could research it, research isn't going to help you here. Okay.
Okay.
The reason is because this is I there's many problems with this, but I just set you up with one of them. What happens when that caterpillar goes into the chrysalis? It turns to goo. Okay.
Okay.
Now, and then it reforms as a butterfly. Now, how does that happen in a millions of years step-by-step process? If you're going to turn to goo, you better have a plan to get yourself not goo. Okay. And you don't have millions of years to collect mutations to help you form yourself into a perfect butterfly. And by the way, caterpillars cannot reproduce. So you have to become a butterfly so that you can reproduce. So you don't have
All right.
millions of years. You have your lifetime as a caterpillar to figure out how to get this done. Okay.
Okay. All
So
right.
I would love to hear an evolutionary explanation for that.
Now, somebody might say, crystals in space and now butterflies. This is what you're combating me with. But this is a problem, I think. I mean, I have to really think about this. I don't think I have any explanation. I mean, so
Yes.
we're gonna have to have some helpful unfair friends tell me a little bit about this biology here.
But that's the thing is like, I tried looking at the evolutionary explanation for this. I used AI. I tried there was no explanation for
Okay.
this. Okay.
Well,
And so if anybody comes up with one, great. But right now, as far as I can tell, there's not one on the books. So and this is just one, guys. I could pick any number of creatures and point out the same types of problems.
yeah,
But I'd
it's a
like to
chicken
zero
and an
in
egg.
on one. Why not? Let's just go
Yeah.
one by one and show how all the creatures that God created could not have come about by a step-by-step process. All right.
Okay. All right. Well, the gauntlet is thrown on this one. I mean, butterflies. Butterflies will be in my doing. Wouldn't that be very poetic?
Yeah.
All right. Colors of the rainbow.
All right, so you've got a week to think about it, Nathan, and let's just see some comments. I want to see if Jeremy started any comments for us. So if Pigs Can Fly says, this is Matt. He says, I am glad your brother is so humble. Thank you.
Well, I'm gonna eat some humble pie here in a minute. It's gonna be butterflies. Humble pie.
Yeah, so Stephanie says, y'all are pretty cute as brother and sister. Thank you very much. And yeah, you guys in the live chat, we will, especially if you oh, and Pigs Can Fly says, are we able to join? Not on this one, but we can. I would love to talk to you sometime. Let's have a stream together, please. And he wanted to talk about the electromagnetic field degradation. And maybe at some point we can have unfair friends join the stream and talk about it if they want, if we phone a friend or something. I don't know. but we didn't plan that for tonight. So anyway, thank you guys so much for coming. Appreciate your participation. And we do really want to tap into other people's expertise, because me and Nathan are not experts in any of these fields. So we would love if you have knowledge about an area that we're talking about, then please do just put your comments in the under the in the comments on this video, or join us live and put in your chats. And thank you guys for watching. Have a good night.
Bye.